Hello everyone, good afternoon and welcome to the 11th sessions of the editions of MasterTalks. Today's will be dedicated to the Department of Physics. I'm Rafaela, a master student here at Technico, and I'll be moderating this talk. We'll have some time for your questions at the end, and we encourage you to know more about international opportunities and enrollments in the Masters. First, I would like to thank you, Professor Vítor Cardoso, for accepting our invite to be here with us today. Professor Vítor is a distinguished professor in the Department of Physics here in our university and a board professor at the Niels Bohr Institute at the University of Copenhagen. His main field of research is gravitational waves and black holes and the physics of space, and he is a pioneer in black hole spectroscopy and tests of Einstein theory. He is an author of a book and hundreds of articles published in international journals. We'll have the pleasure to hear what Professor Vítor has to say about some open questions in physics and how we as students can be part of answering them. Thank you very much.
Thank you. I'm really, well, thank you. Oh, wow. Yay! Well, first of all, thank you. I'm really delighted to be here. It's a wonderful summer day outside, but it's cool in the room. Before I start talking about what I want to say, I'm going to be very brief. I'll just try to explain what exactly are the things I think about. But I was coming to this room, I was thinking about my own master. And so I think it's important to share for a few seconds what I thought about my master's. It sucked. I made my choice without knowing what I was getting myself into, okay? And that it was a very tough problem, was axiomatic quantum field theory. So this means that after a few months of working, I thought, damn, this is just too difficult for me. Maybe I just wasn't cut to do physics, okay? So I struggled for a few months until I did whatever people told me to do, but I realized this is not the way to go around things. I'm not doing something I love. I'm not doing something that I'm excited about. And so either I change my life or I should do some construction work out there. So I changed my life. So the second thing I would like to say before starting is you're in a fantastic university and institute. Really, the students are the best, or one of the best Europe-wide. I haven't seen yet a place with such brilliant students. I'm in the Niels Bohr Institute in Copenhagen. I swear there's no comparison. I hope there's nobody from there here. So I am really excited. And I'm going to talk a bit about physics just for a few minutes. And in physics, we try to understand the things around us, okay? So we try to look at this room and somehow understand the fundamentals of the room. And we tried, you know, we've been trying this since mankind came to be. And we realized it's really just way too difficult to explain Joanna or Luis or whoever else is here. It's just, our brain is not good enough, okay? So explaining people, explaining relations between people, explaining a tree to the level of detail that we want, it's just not possible right now. So a few thousands of years ago, we gave up on this ambition, and we thought, okay, let me not try to explain Luis. Let me instead try to see if there's some common building blocks among all the things that we know and that we see. And after 1,000 years on this quest, 1,000 years is a lot of time, okay? We realized that we could explain everything. Well, we don't know where matter comes from, but it's okay. If we assume that things exist, okay, then we can explain everything with just 4 fundamental interactions. We gave them some names. The electromagnetic interaction, electricity and magnetism, the weak interaction, the strong interaction, stuff that happens on small scales, nuclear kind of things, and my favorite one, and I'll tell you why it's my favorite, the gravitational interaction. We can explain everything. It's amazing, okay? And we've been, of course, trying to as centuries go by, trying to explain at different levels of detail the things. So let me go through give you a 10-second kind of overview of the things we learned. This is also actually an instructive kind of diagram because you realize where we're going, okay? And so, for example, we understood mechanics since we started looking at how things move, how things fall. We kind of know how it works. We can predict things. And this happens, at least it happened, on scales of a meter. And we started looking at small asteroids, stuff that's gravity is not important, the electromagnetic interaction is important, and those are scales of a kilometer or so. Okay? And when the last century started, we thought, shit, we understand everything. It's amazing. We're gods, we can build everything. But then we started looking out there. So in the 1900s or so, and we realized things were not moving as we thought they should. Okay? We still don't understand what's going on. We give it some fancy name. We say there's some dark matter out there. It means we either don't understand gravity or we don't understand matter. We don't know what's going on. Okay? Then in the 2000s, we looked further beyond on even larger scales and we realized, God damn it, we really don't understand how things move. And even this stuff that we call dark matter is not enough to explain it. So we gave it yet another fancy name. We said, well, maybe there's something called the cosmological constant. And that's making our universe expanding and expanding at a faster rate the more time goes by. Okay? So this is 2000s. In the 1920s, we started going small scales. Okay? And we realized, oh, this is cool. Now I see structure in an atom. We build what we call quantum electrodynamics. Again, just fancy names, but to explain the things on very small scales. And in the 1950s and 70s, we started going even on smaller scales, and we started realizing what happens to the strong force. Okay? In nuclei, in atomic nuclei, we understood quantum chromodynamics in the 1970s. We still don't understand it fully, but at least we have a very good idea. I want to talk to you a bit about gravity and why we should be doing this in 2024. Okay? This is why I put this diagram here, because you see, as time goes by and you see different scales, we always find different things. It's like when we left Europe, we went to Africa, we means European, of course, to Africa, to the Americas, there was always some kind of beast, a new beast out there. It's the same with the universe. Each time you go elsewhere, there's something there for you, something new, okay? So, if you think about gravity alone, we can measure gravity, we can quantify gravity by how strong the gravitational force is. We don't actually measure gravitational force because that scales with the size or the mass of things. So we use instead the gravitational potential. I don't want to write equations, otherwise you'd kill me. But the point is, this thing that I'm calling gravitational potential is a very small quantity at the surface of the Earth, around 10 to the minus 10. 0, 10 zeros, and a 1. A very small quantity, okay? 100 years ago, we started actually going to regions, that's the surface of the sun, where gravity is super strong. By super, I mean that the gravitational potential is of order, oh, I like this, is of order 1 part in a million, 10 to the minus 6. That's large. We saw interesting things. We saw light falling close to the surface of the sun. Really impressive. We waited 10 years or so, okay, and all of a sudden, we were looking out there because we had better telescopes. Astronomers were telling us, look, I found this star. This is not a normal star, okay? A spoon of material of this star weighs as much as the Serra da Estrela. It's amazing. Maybe I'm crazy, but this star should not be there, okay? So we saw white dwarfs and neutron stars like 50 years ago or so. And they have gravitational potential, which is, you see, billions of times larger than the things we see on Earth. Billions of times. We're probing, we're going to America in gravitational potentials. It's a huge thing. And 9 years ago, we started having instruments that place us in regions where this gravitational potential is not 10 to the minus 11, it's 1. We believe this is the largest gravitational potential in the cosmos. We have no idea what's going to happen there. I'm just telling you, we have a boat that goes to this place. Okay? Now, of course, if you're thinking about doing a master's or actually just reading a book on this stuff, you'll want to know, oh, okay, that's curious. But, well, maybe there's nothing there. But we know there must be something there. Where's my pointer? We know this because I lied to you. We cannot explain everything with the matter that we see on Earth and with the 4 fundamental interactions. We just can't, okay? Unfortunately, we failed. As a physicist, I'm a failure. And we know this because, you know, we've been looking at the motion of stars for roughly 70 years. They should move in a way that we can predict very well. We know the gravitational interaction, we thought, very well. We know how to predict where things are going to be, and they just don't follow the rule. Okay? Stars in galaxies are not moving as they should. And it's even worse than that, because we're so good that we started building the universe as it was born to our day, okay? And the only way we can get galaxies, stars, and planets like the Earth to form is if we add some ingredient to this business, a secret ingredient that we call dark matter. You know, the same ingredient that I spoke before. We need to add some, well, actually it's not some, it's a lot of it. If we want to build the galaxies that we see, and if we want to build the stars that we see moving out there, we need a lot of dark matter. So the standard model, this is really made of electrons and protons and whatnot, the things we can build and we can manipulate on Earth, cannot be the final word. There's something out there, we don't know what it is. Okay? Now, fortunately, we know that gravity exists, and there's a very special property of gravity that we think will allow us to answer what's going on here. And by the way, if you think about this issue, it's kind of interesting. The only way we know about dark matter is through gravity. We haven't seen any secret ingredient in electromagnetism, in the weak or in the strong force. Gravity. There's something with gravity. By the way, interrupt me. It's an informal thing. Now, if you start thinking, if you want to know about gravity, the first thing you'll realize is first you want to know the definition. What is gravity? And then you want to know what does it do. Okay? And the first thing I think that you'll realize is this. Let me play a movie. This played on BBC, was done for a specific show. I actually talked to the producers of this stuff. So they went to the US and they placed a vacuum. Maybe some of you saw. They placed a vacuum in the large chamber and then they let things fall because that's what gravity does. Okay? They say it's a near perfect, more or less. It's a very good vacuum. Okay? And the idea is to let 2 very different objects fall. In fact, they're going to use a bowling ball, just your run-of-the-mill bowling ball, and some feathers, because people always ask about feathers for some reason. Well, the reason is normally they don't fall in the same way, okay? Now imagine that I'm here on the bowling ball and you are here on this feather, okay? And we're just falling. Can you imagine that? I'm looking at you and I'm giving this talk with my pointer and say, you know what? I think we're falling. And you'll say, oh, it must be crazy, man. Maybe you drank some wine, because I see you right in front of me. How can you say you're falling? And so you see, the magic property of gravity is you can turn off gravity. Isn't it amazing? Free fall gets rid of gravity. And Einstein realized this was such a special thing that he called it the equivalence principle. It's like promoting something that you see in everyday life to kind of a religion. That's the equivalence principle. We don't touch it. I don't have time to tell you, it's so easy to say I don't have time to tell you. But it's very easy to use the equivalence principle to show that clocks that live here on the surface of the earth, okay, are slower than clocks that are on the first floor. The tic-tac of clocks on the first floor is faster than the tic-tac of my clock. This was measured. In fact, I have a colleague at the Niels Bohr that measures tic-tacs of clocks which are a centimeter apart from each other, higher in gravity. Gravity makes clocks tick slower. So I like to say that my feet are younger than my head, okay? Which is true to some extent. So we know this about gravity. Last year, we made the most perfect measurement of this fall. We know things fall, everything falls in the same way. You don't want to know with how many digits. It's impressive. There was a satellite orbiting the Earth for a few years, and we let things fall. Okay? So we know, to some extent, how gravity works. Unfortunately, our best description of gravity, it's like I'm always saying bad things. We never know everything. Our best description of gravity is called general relativity. Okay? It was formulated by Einstein. And unfortunately, or fortunately for me and for people who want to do a master's in physics, it cannot be the final word. So not only we don't understand matter, you see, because there's something called dark matter, we also don't understand how matter talks to itself via gravity. And the reason we know this is the Nobel Prize in Physics in 2020. So Roger Penrose proved the following theorem. Okay? The following theorem is this. If you take reasonable matter, like Vítor Cardoso, okay, you smash Vítor Cardoso into a pulp, okay, and when the gravitational potential at my surface is of order 1, is very large, then you form something that I'm going to call a black hole. Okay? Inside that black hole, in the interior of Vítor Cardoso smashed to a pulp, then either the space-time, the geometry, the things, the fabric where things live, or the theory, they go to hell. Something goes very, very crazy when you form a black hole. Okay? So we don't understand gravity when it becomes very strong. That's the summary of the Nobel Prize in Physics in 2020. Of course, there were actually 3 Nobel Prizes. The other two people, Andrea Ghez and Rainer Genzel, they actually showed that these places exist. They didn't take Vítor Cardoso, they took something a bit larger, but they showed these things exist. Okay? And so, when I started my PhD, the idea was simple. Well, if Einstein is wrong, how can we correct it? Okay? There must be a way. Okay? And I'm not going to detail, but I want to show you that at least I tried to do something serious. And so we know Einstein's theory needs to fail, but thousands of people before me and before you try to improve on that theory. The problem is that there's this beautiful result in 1971, I wasn't even born, okay, that says that the theory, the mathematics that Einstein wrote is the most beautiful, simple, and elegant thing. I'm not going to translate this to mathematics. I don't want to do that. But it tells me, if you want to correct Einstein, you need to work very hard. Okay? You need to put something there that is going to sound a bit weird. And so there's thousands of people trying to do that. In fact, there's a meeting going on, well, actually right now they should be above us, discussing how we can try to do this. Nobody came up with an answer. So that's something for some of you, I hope. Okay? So matter fails, gravity as we know it, the description of gravity fails. And so this is all bad news. No, it's not. It's good news. But I want to give you the other piece of good news. And the other piece of good news, it's a gift that we didn't even know we had, and that's built into Einstein's theory. The gift is the following. Mathematics. The gift is the following. Einstein's theory, each time it creates a black hole, okay? Each time a black hole forms, whatever a black hole is, the theory, the mathematics say, it's the simplest object in the universe. This means the following. I want you to think this Cardoso guy is clever. He wrote an equation. So I wrote an equation. And the equation says that any black hole in the universe, any, is described by only two parameters, okay? The rotation, the angular momentum A, I'm calling it A, and the mass M. Any of the trillion of black holes out there are totally characterized by these two guys, okay? And I'm sure you don't realize how special this is because you're just there listening to the talk and maybe believing in what I say or maybe not. But if you start thinking how to characterize me, then you realize, oh man, this is something. Because if you want to go home and tell your mother, oh, I saw Cardoso, and she'll say, okay, how is Cardoso? Well, 1 meter 75, 70 kilos. Okay, good. What is he dressing? Well, he had this weird shirt and some sneakers with red shoelaces. All right, good. And is he hairy? Well, yeah, maybe a bit. Does he carry glasses? Yes, he carries glasses. What's the color of his eyes? Well, they're greenish, bluish, I don't know. Did he shave? Yeah. Did he have a clock? Yeah. Did he wear socks? Yeah. And so you see, if you want to fully convey all the information about me, you can spend a lifetime. You can spend, in fact, trillions of lifetimes, and you'll not be done. All the black holes in the universe are roughly the same. Mass and spin, and you're done. It's almost unbelievable. They are the simplest things out there. And therefore, they make our life easy because you can use them as tools. You know, if they actually exist, well, then it's easy to see, well, so to speak, how things behave around them, how gravity is different from the prediction of Einstein and so on. They're amazing. They're amazing, really. And the worst is they exist. Okay? Over the last 24 years, we've been taking snapshots of the center of our own galaxy, the Milky Way, and we see this. Actually, this has like 10 years. We have new, better ones, but for the point, it's enough. Okay? So when we zoom in close to the center of the galaxy, we see all these bright dots. Yes, our telescopes are this good. Okay? We see bright dots, and these are just stars. Okay? And if you start going in the center of this stuff, you'll realize that stars, all of them, seem to do the same thing that the Earth does around the sun. What does the Earth do around the sun? Well, it orbits. Right? You follow the orbit, and it's kind of an ellipse. Almost perfect ellipse. And so if you look at these stars, you will see that they form ellipses, and any high school student, even me, can use these snapshots to do a calculation and calculate what is there. Okay? And you'll realize it's really a 5-minute calculation, roughly. you'll realize, because you know, well, I won't go to details. It's a challenge. But you realize that here there must be something that we don't see that has the mass of 4 million suns. 4 million suns. Each of these guys is roughly 10 solar masses, okay? But there must be something there, a beast, a monstrous beast that we cannot see, that has 4 million suns inside of it. They exist. So these are supermassive black holes. All the galaxies have this. They sunk as the universe grew. These massive guys, they sunk into the center of galaxies and they stayed there. They're doing things in the center of galaxies. I'm not going to tell you what they do. It's very nasty. But they are controlling the galaxy. Okay? Oh my God, I'm not going to sleep tonight. But 9 years ago, we saw not these supermassive beasts. We saw lighter beasts, lighter black holes. Okay? And we saw them, funny enough, because we knew all the 4 interactions. The electromagnetism, the strong force, the weak force. Okay? And when we studied the electromagnetic interaction, one of the things, the main things that we learned, is that when you shake matter, electrons and protons, you generate something. We call that radiation, electromagnetic radiation, light. Okay? Every time you shake matter, you create light. What Einstein thought is, oh, well, that's nice. I have my mathematics. Can I shake mass? So he did that in 1915 or so. He started going to the mathematics and shaking mass, shaking his hand in the paper, of course, in the equations. And he realized that when he shook, it's a figure of speech, of course, when he shook mass, if a star was doing this, there was something being radiated. There was a new type of radiation that we call a gravitational wave. It's not an electromagnetic wave, it's a gravitational wave. And it took us 100 years to actually show that gravitational waves exist. Okay? Actually, I was in this, so there was a detector built in 93 or so. I was there in 2005 when the detector was being perfected, okay? Was improving in sensitivity and so on. And by coincidence, the US Army was also there when I was visiting, because they wanted to lock the facilities, because the instrument was so sensitive that the US Army wanted to use it to understand what was happening across the globe in North Korea. Okay? It was a very weird day. What the hell? I mean, we're scientists. We're not doing anything bad. Just leave us alone. So this is what we saw in 2015. There's 2 black holes a giga light year away, okay, from us. We didn't see this, actually. This is really just a numerical simulation. There's thousands of stars in the background of the black hole, okay? The light is being deflected. That's why you see all these weird shapes. Gravity works as a lens for light, okay? What we saw was this. Let me play this again because it's so nice. What we saw was this detector. This is where I was, actually, okay? There's 2 big arms. There's a mirror at the end of each of these guys, and there's a laser beam going across. There's vacuum. This is the most perfect vacuum in the universe. There's a laser crossing these arms, okay? And when the gravitational wave comes, gravitational waves are just forces, gravitational forces traveling at the speed of light. The mirrors move. Of course, you can't see it moving, not like this. I mean, if it did, we'd probably be dead, okay? You see the mirrors moving by a fraction of the size of an electron. That's what we saw. The technology is so good that we can see this, okay? In fact, the plot, if you wish, that was the 2017 Nobel Prize is this guy. This tells you how much each mirror in that tunnel is moving. Okay? I didn't put units here, but they're here. 10 to the minus 21 meters. It's 1,000 times smaller than the classical size of an electron. It's minuscule. Okay? It's so small that when the people running the instrument put this out among themselves, everybody stopped and said, no, this cannot be true. This looks too good. This looks too much like what we expected to be true. Maybe the Russians are kind of doing something to our instruments. So they locked the instrument for a couple of months until they were sure there was no external interference. Okay? So this is what we saw. This was September 14, 2015. We're celebrating a decade of gravitational waves next year. It was generated a gigalight year ago. Okay? There was nothing on Earth except single-celled organisms. And we had two black holes, each with roughly 30 suns, colliding and sending a huge splash of radiation out. By the way, the splash means that in a fraction of a second, this stuff burned 3 suns. It converted the energy of 3 suns into gravitational waves. Okay? So this was 2015. I think I still have 5 minutes to tell you about what came next. And what came next came 2 years after. We were listening to gravitational waves. We had our telescopes on. Okay? So our telescope was Fermi. It sees gamma rays and X-rays. And we had the same instrument, LIGO, just on all the time. Okay? And we saw this event. It's not two black holes. It has a sound even. This is a gravitational wave and the gamma ray. So we saw a gravitational wave, and roughly 1.7 seconds after, our telescopes started getting light from exactly the same spot. Okay? And the first thing that people ask me is, oh, this is nice. Can we do something with that? And the first thing you can do is calculate. This stuff was really far away. Okay? Really far away. And yet, the time delay between gravitational waves and light was only 1 second. So this means that gravitational waves travel at the speed of light with a precision of 1 in 10 to the 15. So this was an amazing test that gravitational waves do travel at the speed of light, and that's something in Einstein's theory. This is how the event looks like, actually, the best fit waveform for this event. There are 2 neutron stars. They don't look very luminous, actually, but I just enhanced the luminosity. These are gravitational waves. But you see these are jets of matter going on. In fact, yeah. Actually, we learned in the last 3 years that when 2 neutron stars collide, most of the heavy elements in the universe are born here. We had a problem. We didn't know how to explain why we see this much gold in the universe, for example. This produces more gold than the entire mass of the Earth. Okay? And that's something we only learned after we saw this. We do spectroscopy on the emission of these guys, and we see very carefully and precisely how much matter and which sorts of matter is there. This event, let me just give you a quick glimpse of this, was in August 2017. We were really lucky. We have, so far, we've been looking for 5 years now, actually more, and we've only seen an event like this. It's a really precious thing. We hope to be seeing another one in 5-10 years, but so far it's the only guy this loud. When the stars collided, dinosaurs were roaming the Earth. And that's also impressive, no? To think that this was happening and we weren't even here as a species. You know, the wave was traveling across the cosmos. Our civilization was forming, was born, was thinking about these issues, built a detector, the wave comes here, and we're here ready for it. It's amazing. As I said, these are the limits on gravitational wave speed. It's really close to the speed of light, okay? And so this more or less concludes what I wanted to tell you, which is, it's not, we didn't fail. Of course we didn't fail. We know, we have a very good understanding of the universe. We have a very good understanding of what we need to do to reproduce all the things we know, we've seen. But we've also learned that most of the things that we actually see out there, away from the Earth, are not known. We don't understand them yet. We know they exist. We know we have the tools to go after them, but we're just too stupid right now. Right? I mean, we've known dark matter for 7 decades. We know that general relativity fails since the 1950s. Okay? We're not good enough at doing the mathematics, but now at least we have an instrument that allows us to go there, study in detail how Einstein fails, and hopefully, because physics is about observations, we can learn things. Maybe we learn how many black holes are in the universe. How is it possible to form a 4 million solar mass black hole? How the heck does this happen? Who put that black hole there? You know, when? Are they really, as Einstein predicted? They can't, because the theory fails in the interior of black holes, right? Can we use gravitational waves to understand when they were born? How was the universe when these monsters were born? Can we actually use black holes or gravitational waves to learn about dark matter? Because it's dark, but because everything falls in the same way, that's the equivalence principle, even dark matter needs to fall in the same way. Maybe we can use this and gravitational waves to test these ideas. But of course, for somebody like me, who's been around for as long as dark matter, well, yeah, I think this is not what drives me. What drives me is that we're building telescopes now that are going to see things 1,000,000 times better 10 years from now. So in I don't know, 2035, 2040, we're going to have an instrument that makes LIGO look like a blind man. We're going to see things. We're going to hear things. We're going to be seeing the universe. I don't know. I mean, I hope that the instruments we're building now will actually show that there's weird stuff out there. There's beasts out there I can't even dream of right now. So now coming back to the masters, really, there's never been a time in science, in physics, like this. Okay? Maybe we will see nothing, but the chances for nothing to happen are really small. Okay? So it's a fantastic new world out there in gravity, but also in all of the things. In quantum chromodynamics, we are trying to understand now how to solve the equations. There's a lot going on. So welcome to the new millennia. Thank you.
Thank you so much, Professor. First, I would like to start if you have any questions to the audience. If you can, just ask, okay? So,
tough questions, please.
It can be a curiosity about Professor's work, or at least I have a question also. Do you want to start? So, I was curious to know, why did you choose physics at the first place? Because I think a lot of people don't choose physics because they're scared. It's like, I hear you talk about such like amazing and interesting things, and I'm like, that's interesting, but can I do it? Because it seems so difficult and impossible.
Well, there were good. So I think there's two stages of choosing physics, right? The first is choosing physics when I came to university. The reason why I did it was because I could. actually. I think the answer is I chose physics because I knew I was good at doing physics, or I thought I was. And when I was growing up, the world was a very chaotic thing. Portugal, I guess, was chaotic. But my world was very chaotic. There was no control over anything. You know, it was a grown-up world. People told me what to do. I did it, or I didn't do it. But I didn't understand. There was no predictability. And so doing physics was like, you know, you do A today and you get B. If you do A tomorrow, here or in China, you're also going to get B. So I understand those rules. You know, you do something, and for a reaction, you always get the same feedback. So I understand those rules. I like those rules. But of course, you get to university, and I thought, oh, I'm smart. I understand how to do the calculation. And of course, you get to the university, and you think, man, everybody's smart. So of course, that's the second stage, where everybody's their own genius, and you come to university, and you think, okay, am I good enough? Am I as good as him or her? And of course, some colleagues don't measure this in terms of being good or bad. That they just like what they do, and that's fine. But to me, liking also needs to include I really must be good at that. If I'm not good, I just give up. So I don't do anything else with physics. But so actually, this is why I do black hole physics, because there was this colleague choosing the master when I chose quantum field theory in an axiomatic setting. You don't care what that is, okay? But I chose it because there was this fellowship, so I was making money out of it. And like, oh, okay, well, there's money, I know, that's good. And there was a colleague that was starting the master at the same time, and he chose particle physics, and he told me, you know, I would like to do black holes, but it's just so difficult. And that's when I decided, oh, difficult, I need to go there. I need to try that. So it's because I thought, well, if he thinks it's difficult and I'm good at it, well, maybe there's a niche that I can explore. Maybe there's things for me to learn. Yeah.
Well, I have the microphone now. There are a couple of things that are very interesting because they are very counterintuitive for all of us that we are not physicists, which is you talked about the four forces. And the single force that we can understand because we can feel it, you tell us that that is the force that you know the least, which is very counterintuitive for non-physicists. Yeah. Another thing that's very boggling also is that you know that you only know the visible matter is 5%, and the other 95% you don't know what it is, but you know exactly how much, which is amazing. You know how much you don't know, but you don't know what it's made of or how it's arranged, which is also, how do you get there? How do you know how much that you don't know and how much do you know?
So that's
and the third part is, this is very mind-boggling, and this takes me to the real question, which is, how does a physicist work? Do you think? Do you write equations? Do you do mathematics? How do you work? You know, because a mechanical goes to there's a shop and he does What do? You think? You write equations? You write mathematics? What do you? How do you know about the world?
So I have a comment regarding the things with which we are familiar. Usually, I mean, if you look around at your family, especially, it's the things with which we are more familiar that we tend to think the least. So go home and hug your father. So in fact, we know the sun much better than we know the earth. Okay? And I think, well, I suspect that one of the reasons why we know so little about gravity is because we're born and we die with it. It's so familiar, like, well, I don't know if I want to think about it. Like, give me something I can't see. Give me like the strong force. Oh, that's exciting. That's new, right? And so, of course, there have been people thinking about gravity, but it's one of the reasons. We tend to go, the most exciting things are the new things, right? So we know about dark matter because I told you that we look at galaxies and we see stars moving faster than they should. We measure the mass, okay? We put it in Newton's equations, and we know the force that's acting on stars. So we know it should move. but the dense stars are just moving faster, okay? And so this means we can calculate very precisely the mass that takes the star to move faster. But whether the mass is caused by a Cardoso, a Luis Lemos, a Joana, we have no idea. That's why we call it dark. It's matter, it creates gravitational force, but if you look at the gravitational interaction, it doesn't care about the color of my eyes. It only cares about my mass. It's the only thing we know about dark matter, is the mass. Okay? And it happens that this amount of mass that we need is very precisely the same that we need the universe to be born with, such that it creates galaxies and then stars and then people like us. So everything is very consistent. We just don't know what the hell it is. And then you ask me, how do I work? And I asked this question actually to many colleagues because I'm interested in how people work, how the brain works. And we have very different ways. In my particular case, I spend most of the time, well, I used to at least. Maybe I'm lying to myself. That I still, most of my time just looking out the window and thinking about the question that I want to ask, about the problem that I want to solve. And then when I think about the question, so the question takes me a year, let's say, to come up with. I'm looking, for a year I go to my window and I look outside, oh, no, I'm just kidding. I'm thinking about the question. And then usually when you come up with the important question, solving it, I mean, it's really just a question of doing mathematics. Most people, on the other hand, or some people, on the other hand, think that actually doing the calculation is more important, even if they're answering a question that nobody cares about, right? So it's different ways of working. I'm not so much interested in the technicalities. I don't want to build a car. I want to drive the car somewhere. Where many colleagues, on the other hand, think, no, I'm just going to build this Ferrari and then I'll just leave it there. And that's okay. They show their, they have this technical prowess. It's okay. But so there's different ways. So most of the time I'm thinking, of course, thinking means you sleep with a problem, you wake with a problem, you sleep with a problem, you read, you sleep with a problem, you read, you walk, you talk to colleagues, you go to meetings until that darkness in your brain kind of crystallizes. Aha, this is it. Now I understand. Now I understand what I want to go after. And then, okay, then it's a question of getting the machinery, all the necessary skills to actually answer that thing. It's a very interesting process. You have to be strong mentally, because otherwise you kill yourself. But of course, actually, teaching classes is wonderful for this, because you go there, and at least for some hours during the week, you have these, 100 brains in front of you, all seem smarter than you, always asking questions that you don't know the answer to, and that forces you out of that problem, right? You go into their brains, and like, man, how do I answer this question? I had a student who was always interested in vertices. I was doing the electromagnetic interaction, and that guy, oh, but what happens if I have a square? What happens to the electromagnetic field? And then I would go home and, what the hell? How do I answer this stuff? And so that's useful. Your brain goes outside for a few hours or a few days, then you come back to the problem, and, oh, I understand something now. While you were answering the student, the brain was doing some things. So it's a very interesting, I think, mental process. Come on, don't be shy.
Okay. Just for the mic too.
So I have two questions. The first one was, in these detections, so in 2015 and 2017, did we had any prediction that we might detect something at that time, or was it just blind luck?
Pure luck.
Okay, and in the future detections as well, so we have no idea if...
No, so we don't know where they are. Okay? We have no idea where they are. They're black, really, so we have no idea, but we have a very good idea of how many there are now. So we know, I'm just going to throw a number. We know to 1% how many of these events we're going to see per week. We have a very good idea. In fact, I was talking to the person that was on duty on that day. He told me he almost fell off the chair. Okay, he was looking at the screen, and that signal that it's exactly what you see on the screen. And the guy was like, I was falling off I was screaming through the laboratory. I was calling everybody, waking people. He was in Germany, waking people back in the US, and nobody could believe it was true. So we shut the instrument, and like, Russia is trying to screw us. Let's just get this straight. So they worked for a couple of months until they understood, no, this is real.
And my second question was if you ever just thought about giving up, if there was ever a moment where you just thought that everything was too difficult and you would never be able.
I think that almost every day. Well,
Okay.
not every day. Okay, so that's a very interesting question. So I thought about giving up maybe twice in my life, really seriously giving up, okay? The first was, I shouldn't be saying these things. And there's a record there. So twice in my life. The first was in this master actually choice. So I realized I didn't do I didn't inform myself as I should have. Okay? So I admire all of the students now. They know everything. They know more about me than I do. Okay? So it's really a thing to be excited about. I, on the other hand, didn't ask for any information. I just saw, there's a fellowship here. Maybe I'll take it. And I realized I didn't like the topic. I didn't like so much the supervisor. I didn't like the interactions with the supervisor. I hope he's not around. With a gun. And so it was a year of nightmare. And I thought, well, if I don't recover from this, this is my life, you're at the end of the university, and if you think, I suck at this stuff, I didn't get ready to do anything else. My mother was like, come here, there's a supermarket here, you can be a cashier. And she was serious. That's the worst of it. She was damn serious. Like, no, mother, I'll try just a year more. So I got the PhD scholarship. I'm like, okay, I need to work on this stuff. Now it happened that the first half a year of my PhD was terrible. I had to learn. The project that my supervisor gave me had no solution, and I realized that after 2 months. And then, okay, I'm cashier it is. Until I thought, no, you know what, Vítor, you should come up with your own problem. You must be better than all these people. And so my PhD was basically me giving myself my problems. I don't want to be too unfair. Of course, the advisor gives you the relevant literature, he gives you the working habits. That was really good. Work night and day, don't take weekends, don't take vacations, until you succeed.
That's quite encouraging.
Look, I finished my PhD, I did not know who the Prime Minister was. I finished my PhD and somebody told you know who the... Oh, okay, I believe you. I take no vacations up to this day. And so that was the first time. The second time, this was the first time, there's the second time. The second time was maybe 10 years ago, no more. This was 2005, I think. I was in the US for my first postdoc, and I gave, I really shouldn't be saying these things, but I thought, during the PhD, when I thought, okay, now I'm doing serious stuff. I cook up my problems, people seem to care about them, it must mean I'm good. And I thought, well, it's enough to be good at calculations, at the questions that you formulate. People will recognize you, okay? Somehow. And then I was giving a talk. I had to give a talk in St. Louis, I think. No, it was in Canada, north of Canada. And I realized I got so nervous talking. I was a lousy speaker. Halfway through it, I froze. I didn't know what to say because I was memorizing my talks. I stopped since then. I was memorizing my talks. And somebody told me, you're not making it, Vítor. This is not the level. It can't be like this. I said, no, but it's okay. I mean, I'm really good. My papers are really good. Yeah, but you need to convince people that they need to work on your ideas. And you're not, everybody has something to do. So you need to come here and explain why I should stop what I'm doing and do what you asked me to do, right? And I really was not good. I mean, I froze when and at some point I thought, I really, cashier it is again. But then I took half a year of that, so I was in Mississippi then, close to this instrument. And I started thinking, how can I become a good speaker if I can't memorize? My memory sucks. I can't say jokes, well, I couldn't back then. Say while I'm speaking, so I'm really terrible. But then I realized also that people, when you're there, you just want to be entertained. You just want to have a good time. I mean, I could be here dancing, you don't care. I mean, just, entertain me for a few minutes and you can go on your life. And then I realized that I don't need to go through all, because my problem was the same of giving classes. You're trying to think about all the things that are going through all the brains in the audience. Oh my God, they're going to ask about this, but maybe they'll see this perspective. And then you can't go anywhere, right? And so I realized, no, I'll stop doing that. I'll stop planning anything or memorizing. I just go there and I say the things that I feel like saying. This is the overall idea. I spend a few minutes thinking, this is what I want to say. How I'm going to say it, I'll just make it up on the spot. Apparently, it worked. And so, for a couple of times that was rough.
Thank you.
Delete that.
Thank you.
How will the new instruments work? So LIGO was based on mirrors and vibrations. So how will the new instruments work?
Good. So LIGO is... let me go back to LIGO. No. So LIGO, we see gravitational waves because it's a traveling force. But I told you that things move by the fraction of an electron, okay? So if there's a gravitational wave coming by and you want to measure the distance between these two guys, the key, whatever, and the bottle of water, the gravitational wave won't do anything because there's friction. There's friction and it's such a weak force that you can't do anything. So what you do is you don't do this. The mirror at the end of LIGO is actually suspended. So there's a silica wire that's attached to the ceiling, all of this in vacuum, because you don't want the air molecules to look like a gravitational wave. That's why it's the most perfect vacuum in the universe. And that's the mirror, it's a 1 kilogram or whatever mirror. It's there waiting for the gravitational wave. The reason why LIGO is not that good is that the wire is suspended on the ceiling. But where is the ceiling? Well, the ceiling is in this tunnel, and the tunnel is supported on the Earth. But the Earth is always breathing, is always vibrating. There's seismic activity. That stuff is close to the shore of Louisiana, so there's tides going by and so on. There's a lot of noise because of this activity. So we didn't arrange this question, but I brought this. So LISA, the plan, LISA was started 20 years ago or more. We realized this back then. The only way to get rid of this seismic activity is to remove things from the surface of the Earth. So LISA, this is the instrument that's being built as we speak. It's going to fly 10 years from now, almost exactly. Doesn't have an Earth. It's just 3 satellites here, you see. The laser beam is roughly the same. It's going to be shot at 3 different satellites, but now there's no Earth. It's just going to be orbiting around the sun exactly like the Earth. You don't see the moon. Some people sometimes ask me this, where the hell is the moon? Well, the moon, the instrument is so amazing that you can't even see the moon. This stuff, the LISA, is 10 times farther from the Earth than the Earth-Moon system. Okay, that's why you can't see it. The scales. The arms, you see LIGO has arms of 3 kilometers, the distance from the distance that the laser beam travels. Why? Because to see a gravitational wave, so when a gravitational wave passes, the distance between this stuff changes, but it changes the more these are far apart. So if this is 1 meter away, it changes 1 millimeter, let's say. If it's 10 meters, it changes 10 millimeters. So if you want to see this well, you want to place it far away, okay? So Lisa, instead of arms of 3 kilometers, is going to have arms of 2 million kilometers. It's a beast. It's a magnificent thing. It looks like a lie, okay? It looks like it can't exist, but in 2017, we sent a mini version of Lisa to space, and it worked wonderfully. So we know we have the technology. We know this can be done.
Okay. So, as you said, the more the distance, the more they separate from each other.
Yeah.
So why did that happen?
That's a very good question. It happens because I don't want to ruin my shirt, but gravitational waves are a wave that travels in the, we say it's in the fabric of space-time, okay? This means you take the geometry and its deformations of the geometry. And there's a very nice analogy to my shirt, my beautiful shirt. If you start stretching my t-shirt, so put dots here on the t-shirt, okay? And now stretch the t-shirt. You'll realize that the distance between different dots, when you stretch it, 2 consecutive dots, the distance is always the same. But if you measure the change in distance between the ends of this, it's proportional to the number of these dots, okay? It's exactly the same with gravitational waves. You're stretching the full space-time, okay, in a uniform way locally, so that globally, the more you have, the more you stretch. That's the reason.
Okay. Thank you.
Very good question.
Does anybody else has any questions?
Easier questions, please.
Then I got one.
Oops.
Just at the beginning of your talk, just in passing, you said, okay, we don't know something like this. We don't know where things come from, but you know they happen, and we look at them. So I think you're talking about the limits of physics, of what you do as a physicist.
Oh, yeah, we don't know. So, yeah, I said that we don't know where things from. That means where things come from. That means we don't know how matter came to be. We know where it comes from. We give it a fancy name. We always give fancy names in physics. Well, actually, I think in science, to the things we don't know, right? Oh, it's dark matter. Oh, it's the cosmological constant. I really like these names because we spend a lot of time on this. And we give, so I said that our knowledge breaks down in the interior of black holes. Gravity, we don't know about gravity. And we call it a singularity. It's a fancy name. In fact, the Nobel Prize in 2020 also gave us a nice name. It's a conjecture that wants to save us from this failure. It says, well, every time this singularity happens, I conjecture that the universe produces a horizon, a black hole, okay, that hides the singularity, that hides the failure. We call this the cosmic sensor. But there's another singularity, and that's called the Big Bang, another fancy name. And the Big Bang is really just a word for the beginning of everything, in particular for where matter comes from. We have no idea how, or in which way this forms, or what exactly the Big Bang is, except that the infinities are there. Yeah. So I think the moment we correct general relativity to solve the interior of black holes, I am quite sure we're going to understand the Big Bang. We're going to understand where the universe came from. So maybe we'll understand where we all came from. Nothingness.
Okay, thank you so much.
Oh, there's a.
Do you have any question? Of course.
Is it on? Maybe it's not so quick, but it was just
Good.
that you, during all this talk, we are always talking about how as we go further and further away, everything stops to work. So what happens like the other way around? If we get smaller and smaller, like we define an atom and then a neutron and then 3 quarks and a neutron, and then what happens then? Does it ever stop going down?
That's a very good question. We have no idea, and I don't. So it's no. It's an interesting question actually. It's an interesting question because up until 2000 something, that's exactly what we were doing, right? We were smashing things at higher and higher energy, LHC, and then whatever else. The accelerators to smash particles were becoming more and more powerful, spending the energy of cities because we wanted to see smaller and smaller scales. And now, 2024, we're in a point, I don't think I'm being unfair to anyone, where as a society we say we just can't go on. I mean, we just don't have the wealth enough to continue to producing larger and larger accelerators on Earth. Okay, so we kind of stopped the quest of going to smaller scales on Earth, and the idea is to look out there and wait that the universe gives us natural accelerators that we can use to probe smaller distances. But even then, even there, that's another talk. But we have issues with these small scales. Okay, we have things called the hierarchy problem, the strong CP problem. There are things that we know that we don't understand at small scales, at the small scales that we know. But what I'm trying to say is going even smaller, I don't know, maybe one of you has a good idea, but we really need a good idea.
Just one last thing. I saw somewhere like a chart with like 12 elemental particles or something like that. A certain number of particles that make up everything. Are we sure that's like correct? Like, do we know if it goes even smaller? Or is it another where we don't have enough wealth to find out?
I don't think we have enough. Well, we certainly know that cannot be it. We certainly know because we don't know what's making up dark matter. As I said, I'm organizing a school here they are all focused on something called the axion, which we've never seen. It's a new type of particle that could be dark matter. With the axion comes an invisible vector, an invisible scalar. So my answer is certainly not. We have no idea what are the...
We have one more question.
A quick one, but not so quick.
This one is a quick one, Professor. I have this question which is a bit related to my field of study, which is there is already obviously a connection between the aerospace industry and theoretical physics or the areas of physics that you study. This is one of those examples, ELISA orbiting Earth and the results that come from it. Which other steps or other connections could be made between the aerospace industry and theoretical physics in order to improve our knowledge of the universe? Because we obviously know that nowadays it is challenging enough for an aerospace engineer to think about how we go to Mars, but in the future, having that possibilities or that realities fully developed, what are some areas that could be explored and that could create a bridge between
So even I'm a pure theorist. Okay, so in principle, I'm the kind of guy that would say, I have no idea. That's technology. I mean, but even because I work in pure theory, even I know some of the urgent things. For example, last week I was discussing with a team of people in the US who want to take a detector to the moon. Okay. And the first, a gravitational wave detector, it will be a new detector that's sitting on the surface of the moon. And the first thing they tell me is, but we don't even know the seismic activity on the moon. Something as basic as that we don't know. We don't know what type of material we can get up there, how big the payload we can make it to transport it in a rocket. Can it stay on the visible side of the moon where we know we have a lot of radiation that's going to hit our detector? And if we take it to the hidden face of the moon, how the heck are we going to communicate with it? You know, how are we going to send radio transmissions? The same thing for LISA. One of the things that we know worked well in this mini prototype that I told you flew, one of the things we don't know yet well enough is the impact of cosmic rays. Cosmic rays, when they hit, it seems it's the kind of thing that I, as a theorist, tend to totally forget. Who cares about practicalities? Somebody will fly that. But you talk to people who actually build stuff, and like, well, this is nice, but there's cosmic rays. The cosmic ray will hit, these are golden, well, whatever. There's a mass here, right? There's always a mirror, some sort of mirror, okay? And their question is, well, there's a cosmic ray that once in a while is going to hit the mirror and it's going to remove an electron from it. It's going to be charged, okay? If you sit down for 5 seconds and look at the effects of charge, they're like thousands of times larger than the effect of a gravitational wave, okay? So you need to be sure that you can neutralize this charge as quick as possible, and that's a technological process. I mean, project. It's not, we know the theory, we know everything very well, but you need to make sure that your technology is good enough. So, trying to answer your question from a theorist's point of view, it's a fundamental thing. I mean, understanding how we can take to space ideas that we have for new detectors, I think it is the first step, the only first step that we need to worry about. The rest we'll get there eventually. Okay? And actually, let me finish with this. Many people ask me, I'm always forced to explain why we do what we do. And my temptation is to say, well, I do what I do because I like to know things. Yeah, but who cares about black holes? They ask. Well, yeah, but who cares about Ronaldo? And yet you pay him €1 billion a year, right? Right? So you think, well, just the pleasure of knowing should be enough. But it turns out, by pure coincidence, or pure luck, I would say, that every time you learn something that you only wanted to know just for your curiosity, there's always an application. I mean, it's amazing, right? And so this is no exception, actually. People realized that with the technology that we have to see gravitational waves here, with these detectors like this, what do these guys do? Each time a star moves, right? Suppose my hand is a star. It emits gravitational waves, okay? So this detector will see it. Any mass creates a gravitational wave. Now think about planet Earth. Our planet that Joanna was saying, just to make the point again, we're so familiar with it, we never think about our poor planet. Let's hug Earth. Now if you think, if you think about the Earth, what happens inside the Earth? Earthquakes happen. What's an earthquake? Well, it's a mass moving. There's some dislocation of mass, right? Can you imagine? This guy, now gravitational waves travel at the speed of light. This is an important fact. Seismic waves travel at a few thousand kilometers per second. For those who don't have this in mind, the speed of light is 300,000 kilometers per second. This means that this same technology that is about to detect black holes and whatnot can tell you that an earthquake is going to occur before you actually get hit by it. You can end up saving thousands of lives with something that was built to see black holes. It's amazing, no? So yeah, technology is really important. That's my key message.
Thank you.
So I think we're done, right? So this marks the end of this talk. Thank you very much, Professor. This also today marks the end of our MasterTalks. This is the first edition, so thank you for being part of it. We hope to see you next year. And if you have any questions about the Master in Physics, we have here the responsible teacher for it, Professor Luís Mel. And also, if you have any doubts about enrollments or any questions, we are here, the Student Support Unit, so thank you very much.